What specific problem does the proposed visual reasoning chain, VRC bench, aim to solve in the context of multimodal reasoning, and why is this important for the field?
The proposed visual reasoning chain, VRC bench, aims to address the significant gap in existing visual reasoning benchmarks, which primarily focus on end-task accuracy while neglecting the quality of intermediate reasoning steps. This is crucial because effective multimodal reasoning requires not only accurate final answers, but also logical coherence and sequential problem-solving across multiple modalities. By introducing a benchmark that evaluates step-by-step visual reasoning capabilities across 8 diverse categories, VRC bench ensures a comprehensive assessment of models' reasoning processes. This holistic approach is important for advancing the field, as it allows for better comparisons between models and fosters improvements in their ability to handle complex real-world problems. Ultimately, VRC bench enhances the interpretability and reliability of multimodal models, which is essential for their deployment in practical applications.
How does the LlamaV-o1 model work? Illustrate its methodology step by step, particularly focusing on the integration of curriculum learning and beam search.
The LlamaV-o1 model operates through a structured methodology that integrates curriculum learning and beam search to enhance multimodal reasoning capabilities. Initially, the model undergoes 2 training stages. Stage 1 focuses on generating summaries and detailed captions from input data, using datasets like Pixmo and Geo170K to build foundational reasoning skills. In Stage 2, the model progresses to detailed reasoning and final answer generation, utilizing the LlamaV-o1 dataset to refine its ability to break down complex tasks into incremental steps. The curriculum learning approach ensures that the model starts with simpler tasks and gradually tackles more complex, multi-step reasoning scenarios, improving logical coherence and adaptability. Additionally, the beam search technique allows the model to generate multiple reasoning paths in parallel, selecting the most optimal one, which significantly enhances inference efficiency and output quality, achieving a time complexity of O(n) compared to traditional methods.
Can you provide a simple illustrative example of how LlamaV-o1 generates a final answer from a complex visual reasoning task? Walk through its reasoning steps with this example.
LlamaV-o1 generates a final answer from a complex visual reasoning task through a structured multi-step reasoning process. For instance, consider a task where the model needs to analyze a chart depicting sales data over several months. The first step, task understanding, involves the model comprehending the question, such as, what was the highest sales month? Next, in the task summarization step, LlamaV-o1 generates a summary of the chart, identifying key trends. Following this, the model produces a detailed caption, labeling specific data points like, sales peaked in June. In the logical reasoning phase, it breaks down the task into sub-goals, such as comparing monthly sales figures. Finally, the model outputs the final answer, stating, the highest sales month was June, based on the logical deductions made throughout the reasoning steps. This systematic approach ensures clarity and accuracy in arriving at the final answer.
What are the theoretical and practical benefits of using the proposed VRC bench and LlamaV-o1 method over existing visual reasoning models? Be specific about improvements in performance and efficiency.
The proposed VRC bench and LlamaV-o1 method offer significant theoretical and practical benefits over existing visual reasoning models. The VRC bench introduces a comprehensive framework for evaluating multi-step visual reasoning tasks across 8 diverse categories, emphasizing the quality of intermediate reasoning steps rather than solely end-task accuracy, which addresses a notable gap in current benchmarks. Practically, LlamaV-o1 combines curriculum learning with beam search, allowing the model to incrementally develop reasoning skills while optimizing inference efficiency. It achieves an absolute gain of 3.8% in average score across 6 benchmarks and operates 5 times faster than the LlamaV-o1 model. This structured training approach enhances logical coherence and adaptability, enabling the model to handle complex tasks more effectively. Furthermore, The use of a new evaluation metric that assesses reasoning quality at the individual step level ensures a more accurate reflection of model performance, thereby improving interpretability and reliability in real-world applications. Overall, these advancements lead to superior performance in reasoning-intensive tasks, as evidenced by LlamaV-o1's competitive scores across various benchmarks.
Describe the validation process used for the proposed benchmark and model. What datasets and metrics were utilized to test the effectiveness of LlamaV-o1, and what were the key findings?
The validation process for the proposed benchmark, VRC Bench, involved a semi-automated annotation pipeline to generate step-by-step reasoning responses, followed by manual verification to ensure accuracy and clarity. The benchmark incorporated diverse datasets, including PIXMO and LLAVA-COT, covering various domains such as visual reasoning, mathematical reasoning, and scientific reasoning. For evaluating the effectiveness of the LlamaV-o1 model, metrics included faithfulness step and faithfulness token, which assessed alignment and informativeness of reasoning steps against a ground truth. Key findings indicated that LlamaV-o1 achieved a final answer accuracy of 56.49% and competitive step scores of 68.93%, outperforming existing models like Java-COT and demonstrating significant improvements in reasoning quality and inference efficiency across multiple benchmarks. The structured curriculum learning and optimized inference design were critical in achieving these results, highlighting the model's robustness in handling complex multimodal tasks.
What limitations or drawbacks exist within the proposed methods, VRC Bench and LlamaV-o1? Discuss potential challenges in their application and areas for future research.
The proposed methods, VRC Bench and LlamaV-o1, face several limitations and challenges. Firstly, while VRC Bench aims to assess step-by-step reasoning, it may still struggle with the inherent complexity of visual reasoning tasks, as the benchmark does not fully address the nuances of every multimodal scenario, potentially leading to gaps in evaluation. Secondly, LlamaV-o1, despite its advancements through curriculum learning and beam search, may encounter difficulties in generalizing across highly diverse or novel tasks that were not represented in the training datasets, which could limit its adaptability in real-world applications. Additionally, the reliance on semi-automated reasoning generation and manual verification in VRC Bench could introduce biases or inconsistencies, affecting the reliability of the benchmark. Future research could focus on enhancing the robustness of the benchmark by incorporating more diverse datasets and refining the reasoning generation process to improve model generalization and accuracy in complex visual reasoning tasks.